All right, so for our next talk, it's my pleasure to welcome Rena and Steve.
All right. So I am going to be talking about experiments that we did in superfluid helium in my lab in Davis. It's been experiments over a series of years. Most of it's been done with undergraduates. Ingrid Neumann was the one grad student who got her PhD on the experimental part. And then there's this raft of undergrads, and I've included only the ones most relevant to what I'm showing today. Okay, so the experiment that we do is based on Joe Vinan's old experiment that measured circulation in measured quantized circulation in superfluid helium. And you heard some references to that experiment yesterday, and I'm actually going to go through more about how that actually works. So we have a container of helium. In our lab, it's typically about 5 centimeters long and 3 to 6 millimeters diameter. Should I go on?
Yep.
Okay. Then down along the cylinder, we have a fine wire. The wire that we use is about 17 microns diameter, and this is glued in place under tension. Undergrads are really good at this. It works. So then we create a vortex around, we used to spin the refrigerator. We've now found ways to create the vortex without spinning. But we create a vortex which then will stick to the wire. So the wire itself is the core of the vortex. And then we have a perpendicular magnetic field. So we put a pulse of current through the wire. That creates a perpendicular force. Once the current pulse stops, the wire vibrates as it eventually settles to its equilibrium position. And while it vibrates, we see an EMF across the wire because it's moving in the field. So that's our signal. So what then happens is that the wire has actually 2 normal modes that we're looking at, because the wire could be going in this plane or that plane. Or alternatively, if it's a perfect wire and these modes are totally degenerate, you could view it as circularly polarized modes. Right. Now it turns out that when you put circulation around the wire, the degeneracy between those modes splits, and you end up with circularly polarized modes with slightly different frequencies. Okay, and we basically measure the beat frequency between those 2 modes, and I'm going to show you in real space how that works in a moment. It actually turns out that real wires are not perfect and the modes are not degenerate even before you apply the circulation, and that's just something I don't want to talk about here. Okay, so I'll go through how the Magnus force works, because I have a couple points I want to make about this. First of all, I really want to stress that the wire itself is the core of the vortex. It's not that the wire is moving through some flow field that includes a vortex. It drags the vortex with it as it moves. So what it looks like is if the wire is moving this way and you have a vortex going around it like that, in the frame of the wire, you still have the vortex because that's plugging away with the wire. But now it looks like fluid is backflowing past the wire on both sides. That means that on this side, the 2 velocity fields are partially canceling. And on this side, they're adding, so you have a different flow velocity on the 2 sides. And then Bernoulli's law says that, well, that means that you must have higher pressure over here where the velocity is small, lower pressure on the side where the velocity is big. So the pressure difference is creating a force that's pushing the wire off to the right. And that was completely independent of the direction that the wire was moving in. The reason it's off to the right is just because of the direction of the circulation. All right, and so then the vortex makes the wire's actual path curve. So instead of moving in a straight line perpendicular to the original magnetic field, it's going to move in a funky pattern. And one of the reasons I wanted to put this up was to stress that even though the velocity difference comes from the circulation around the wire, you're going to have a bigger effect if the wire is moving faster, because it's actually the rho v squared term that comes into Bernoulli's law. So when the wire is moving faster, you'll actually have a larger force. And that means that near the center of the wire, vertically, where the wire's motion is largest, the vortex, you're more sensitive to what's going on with the vortex there. Okay, so this is what our typical signal looks like. And it really, this data honestly is typical. It was chosen at random, just based on, this was something at a pretty low temperature. And so the black points are data, the red points are a fit to this. It's a good fit. Okay, and so this is the path that I was suggesting that what the vortex does. It starts off moving perpendicular to the field, but it curves. And then when it comes back, it's still curving to the right, which means it goes this way and so on. So the plane of vibration is actually precessing. And you see a minimum here when the plane of vibration is now moving in the same direction as the magnetic field and you have no induced EMF. So this beat frequency that we're seeing is related to how fast the plane of vibration is precessing around, and that's related to the circulation. So we pluck the wire, we measure this, we do this fit, we look at the omega that comes in there, which is really the beat frequency between the two modes, and we have a way of converting that beat frequency to circulation. Okay, and so years ago, when Joe first measured this, what he saw was that the expected quantum value of the n=1 quantum was much more stable than anything else. Even in the early measurements, that wasn't actually the only thing that showed up. And years later, so in graduate school, I repeated the measurement in superfluid helium-3, which is sort of insane because you need to rotate a bucket of helium-3 at darn low temperatures. But one of the things, helium-3 has a larger core size and some nice things happened, and then we were able to repeat it in helium-4. And so what we find is that sometimes a vortex goes partly along the wire and then actually comes off midway. And when this happens, not terribly surprisingly, the effect that you see on the normal modes of the wire is also a partial effect. So when this happens, we see a beat frequency that's in between what we would see if there was no vortex and what we would see if there was a vortex completely along the wire. Okay, and again, I'm not going to go into the details there, but we have a pretty good idea of how to do those conversions. And this picture, I did want to say that, you know, it's something analogous to a tornado, where the tornado has to come in perpendicular to the ground. Of course, it's not on a wire, but often up in the sky, you can see the funnel bending over. And that's exactly what our vortex is doing. It's what if you want to think about what the flow field is doing, that's the picture that you should have. Okay. So my point about the force is biggest if the vortex is the influence of the vortex is biggest near the middle of the wire, means that we're most sensitive to what's going on near the middle of the wire. And near the center, we basically measure the position of that attachment point. And if we're in the middle, we can measure it to something like 10 microns. I think 5 if we're really lucky and you know everything is going well, but that's the level of our sensitivity. Yes.
So how big is the wire compared to the vortex core here?
So the free vortex core on this part in helium is about 3 angstroms diameter, so tiny. The wire is now 17 microns. So energetically, the vortex very much wants to sit on the wire. In fact, one of the weird things about these experiments is that the vortices don't sit on the wire as much as you might think. We actually had originally used a slightly smaller wire, and we couldn't get a vortex to pin to it reliably. One past researcher, Bill Zimmerman, had used wires that went up to 100 microns diameter, and he got up to n=4 while he was rotating, which again, you would really think that much higher values of circulation would like to sit there. I suspect that this has something to do with the roughness of the surface of the wire that's causing, you know, messing up the flow at the edge, but I don't actually know.
So, is the vortex core completely superimposed to the wire, but the vortex core should be naturally smaller, or is the vortex wiggling around the wire?
No, the vortex core really is, as best we know, the vortex core really is just the wire. Okay. I mean, it's sort of indistinguishable from that. But it's clear from the way the Magnus force works that the vortex is tied to the wire and moves with it. The container is several millimeters. The ones I'm going to be talking about is about 6 millimeters diameter. Right. So on this part, it really is the easiest way to think about it, I find, is just the wire is the core, and then at some point the vortex leaves. And here it has a free core, which is much smaller. Okay. All right. So once you have this situation where the vortex is coming off the wire, you start to see interesting dynamics, because if you have a vortex that's partly, actually, let me go back. Right. When you have this, where the vortex is off the wire, vortices move at whatever, they try to move at whatever the local velocity field is. And in this case, we have a velocity field from the straight part of the vortex that's driving everything around the container. So the first thing that we saw, which at the time was completely unexpected, and we promptly ripped apart the lab to try to figure out what was causing these weird oscillations. The first thing that we saw was these very regular oscillations. And it was much more dramatic in helium-3 because the damping was much smaller, and it was oscillating and oscillating and oscillating. And then it got to the n=0 level, and the oscillation stopped cold. And we went, maybe it's physics. So it turns out that the period here is exactly what you expect if you just calculate the flow velocity in the cell and see how fast you expect a vortex to get swept around. The reason that we see it is that the wire is not dead on the center of the cylinder. That was originally a complete accident. If you try to put a 17 micron wire down the center of a 3 millimeter container, I can guarantee you you're not going to make it right in the middle. So because the wire is off center, this free end of the vortex is actually going to change length as it goes around. Now, on this side, it's quite short. On this side, it's much longer. Of course, this is a very exaggerated picture. And as the free end of the vortex changes its length, the kinetic energy associated with the flow field has to go somewhere. So at this point, where this part of the vortex is short, the part of the vortex covering the wire gets longer to compensate. And that's where we see a maximum. Then you come down to a minimum, and that's where the vortex has gone halfway around the cell. Now it's on the long part for the free vortex. And we don't see the free vortex directly. We only see the part that's left on the wire, which is now much shorter. So one period of this oscillation corresponds exactly to going around the cell one time. And you can see that there's energy loss, which I'm going to talk about in a little bit, as the vortex is moving, which you kind of expect when you have a vortex moving with respect to a normal fluid. I should also stress, I didn't mention this, but after we create the vorticity, all of our measurements are made with the cryostat stationary. Okay, right. Yeah, so let me go on. Right. Another thing that we can see is we sometimes see actual pinning. And here the idea is that you could have roughness, some sort of bump on the wall of the cell. Originally, when we saw this, it just happened. We had no deliberate bump. Since then, we've started to put in a deliberate bump and a deliberate macroscopic bump, and very reliably, the vortex will stay there and stick to it. So if the vortex is doing a lovely precession, this is the same as one of the oscillations from the previous slide. And then it suddenly gets stuck for some reason. It encounters something on the wall that doesn't want it to move. Then it does this. And the reason for that is actually that the shape that the vortex wants to take while it's moving is not the same as the shape it wants to take if it's stuck in place. And because of that, it has to go from one shape to the other, which it does by having these wiggles which gradually die out. This was actually a computer simulation using a vortex filament model where we just said, okay, we have a precession, we set the parameters in it to mimic our actual cell and the data as much as possible. And then at this point in time, we said, now it gets stuck, see what happens. And the computer said, well, it does this. And we said, yep, that agrees. Okay, so yes.
How big is the bump?
So in this case, this was a bump that was just the roughness of the wall, so some sort of microns, and then we now put in bumps that are sort of millimeter size, because that way, well, you'll see. The point of it is that then we can pin it where we want to pin it instead of at some random spot, right? So one of the things to get from this is that even though we're only measuring the attachment point where the free vortex touches the wire, everything's connected. And if you have motion of the free vortex, that gets reflected in the attachment point motion, and so we're able to see it. Right. So I wanted to take a little bit of break to go back and talk about the vortex-wall interaction, which I think Joe alluded to briefly yesterday as well. So the first thing, there's a couple of points I want to make here. first of all, we have this slope, which is energy loss. And okay, we can calculate the total energy in the system, just the stored energy in the vortex around the wire. And then we see from here how fast that vortex is going away. So that tells us what the dissipation is. And it turns out that this dissipation is mammoth compared to any sort of mutual friction you expect from the bulk fluid. You know, like if you extrapolate to our velocities, which are very slow, you get something that this damping is 8 orders of magnitude too big. At our lowest temperatures, it gets closer to 10 orders of magnitude too big. So, so this is not, we're off by a factor of 5. This is crazy off. And so our conclusion is that actually the damping is coming from the interaction of the vortex with the wall. Even though you have this free vortex that's millimeters long and then it's touching the wall at one point, that point is really dominating things. And I often skip this part because it always makes things harder to compare to theory because theorists use periodic boundary conditions, which I'd love to use as an experimentalist. But in real life, you have boundaries, and in a lot of experiments, they matter. What a vortex is doing at the wall may be very, very important. So I'm putting in a plea for theorists to think about that side.
Why do you not get pinning on the wire itself?
I don't know. I don't really, that spot where the vortex leaves the wire is something that I don't understand. If I understood what the heck was going on there better, maybe I would be able to answer your question. Right. So we also know, I'm not showing data on this, but we know that this slope gets steeper as you go up to higher temperatures, which suggests that the interaction is getting stronger. And in fact, we see one very strange thing with pinning at higher temperatures. Well, strange at least at first, which is that actually a vortex tends to get stuck when you go to high enough temperatures. So here we have, so the black curve is temperature, the blue curve is circulation. We started off, I think we had just rotated the fridge here. We started off going to high temperatures and the vortex basically got stuck. Nothing was happening. It was going absolutely nowhere. We dropped the temperature down to about 0.5 kelvin and the vortex worked free. It actually did not stick at n=1 this time and started into a precession almost immediately afterwards. And at this point, we raise the temperature again, and you see things getting noisier. There's one more bit of a precession dip, and then it gets stuck again. And while it's true that this is very, very noisy, it's very clear that this level is different from that level, and this is very different from 0. The bottom here is still at 0.5. So when it goes to high temperature, the vortex then gets stuck, which is sort of opposite from what you might expect if you have a model of pinning as some sort of thermally activated thing. There's an energy barrier, and if you have high temperature, you have more energy to get out of it, so you think there would be less pinning. What we actually think is happening here is that the Kelvin waves that we create along the vortex from vibrating the wire when we make our measurements may actually be contributing to cause wiggles on the vortex that help it depin. And that mechanism is less active at high temperature because any sort of waves on the vortex get damped out so quickly that they don't make it to the end. So we have a second graph of this over here. It's really the same type of effect, but at a much lower temperature. This particular cell had a much rougher wall surface. And here we can see that just going from 320 millikelvin to 400 millikelvin, there's precession, then it gets stuck, and we drop the temperature again and the precession starts. Okay, so this idea that for us at least, the pinning is actually more effective at the higher temperatures was one kind of funny note that we got from this. Okay. So what we're really trying to do now is look at waves, is study the waves on this one vortex line that we have. As you heard yesterday, this is relevant for the lowest temperature quantum turbulence, where the whole change of energy from one length scale to another is thought to happen by interactions between different wave frequencies along a single vortex line. We have a dispersion relation for Kelvin waves. This is on an infinite straight vortex line, which of course isn't what we have, but the dispersion relation works pretty well for describing like the Kelvin wave that I showed you earlier. There's also a prediction for where this instability, where the coupling would start as a function of amplitude. So this is the amplitude of the original wave. This is the wavelength of a vortex, and n is actually the number of half vortices on your segment. The main point is that most of these numbers here, it's order of 1. So basically, you expect something unstable when the amplitude is comparable to the length of to the wavelength of your vortex. Okay, so the setup that we have is we have our wire. The black here represents the cell. We put a bump near the middle of the cell where we have maximum sensitivity. We actually offset the wire in the opposite direction away from the bump so that we try to make the vortex as long as possible to bring the frequencies down into the range where we can measure them comfortably. The lowest mode we think would look something like this. It's pinned on the bump. We know that. And for whatever reason, it's free to move on the wire because otherwise we wouldn't be able to see anything. Actually, one time, I think we saw pinning on a wire. There was one time where we saw something that was incredibly stable, which I believe we interpreted that as somehow it pinned on something on the wire and it never happened again. Okay, that was years ago. The second lowest mode would then look something like this if we assume that it's free to move along the wire. And note that since the wavelength is now 1/3, the frequency would be roughly 9 times higher. Okay, so here's the sort of thing that we've been seeing. Here we're exciting by plucking the wire every 4 seconds. And here we go to exciting by plucking the wire every 3 seconds. And what we see is a very dramatic difference. The amplitude of these waves along the vortex are way higher here. This is a vortex that's actually pinned on a bump. So the amplitude gets way higher here. You start to see a third harmonic really. And if you count this extra period here, it really is 1/9 of the original period, just as you expect. And then the shape here becomes rather funny, and the level seems to change. The level has not really changed. If we go back here, it's going to pop up right to the same value. I'll also note that this is the endpoint motion, and it's huge, right? The endpoint here is actually moving millimeters up and down the wire, which really is comparable to the length of the whole vortex line. So we're looking at the possibility that this actually is a transition between just seeing the lowest mode and now having coupling between the modes. In addition to the higher mode, this signal is just a lot noisier in other ways. So there may well be even higher modes that we don't have the time resolution to really make out yet. Okay. Right. And we can if we go to even higher drives. So we're using a constant amplitude to pluck the wire. We're just varying how often we hit it. We have 9 seconds, which is sort of a default, and you see that this level is the same as that one. And then we have these progressively driving higher and higher as you go that way on the colored curves. And what we're seeing is that we have this sort of nice waves, then it's funkier, it gets into these very big structures, and then they actually start to shrink as you go even higher. Okay, so which I kind of like, because if you're imagining that this is where the different modes start talking to each other, as they start talking to each other more and more, you actually expect energy to leave the lowest mode and go into the higher mode. So I'm actually fairly happy about there being something like a max in the excitation there. Okay, right. And here you can also see that even though there was this dip here, it goes right back to the same level. Now, the dips themselves, I believe, are very understandable from physics that's so basic it's almost silly, which is really that if the straight line were your equilibrium position where you're oscillating around, then oscillating upward means that, well, the part off the wire gets longer and the part on the wire gets longer. And that's just not going to happen because you have to drag in energy from somewhere for that. right? So on the other hand, if you go down, then the part off the wire is getting longer, but the part on the wire is getting shorter, and you can imagine that compensating. So I think it makes sense that when you start to have these large waves, they actually are going this way, not centered around what would be the position if the vortex were not vibrating at all. And the fact that the vortex is then getting longer as it vibrates with larger and larger amplitude could also explain that the frequency, the period here is noticeably longer than it is over here. That's only at a qualitative level. I cannot get the numbers to completely work out on that one. Okay. So just a summary of what we're seeing. So these are the different colors correspond to different pinning events. They were all, we believe, at the same spot in the cell, judging from what the beat frequency was on these. And here we're plotting the average endpoint position, which is basically what that, how far down the center of the oscillations is. And you see that it's steadily going downward, maybe leveling out at the very bottom. The frequency similarly drops, but then does seem to be leveling out. And then we have the actual amplitude of the motion itself, which is small when we're not putting a whole lot of energy in. It seems to go up and have a peak. Certainly the green and the purple curves definitely both showed clear peaks, with, related to the data that I showed you. Okay, and I'm gonna. This is my last slide before the conclusions, and I want to just put out there the thing that I wish the most someone would just tell me the answer to, which is how the waves are actually exciting. I mean, yes, we have a wire that's attached to one end of the vortex, and we're jiggling the wire, but we're vibrating the wire at 447 hertz. And then the beat frequency of the wire is about a hertz. And then we're creating these modes that are several millihertz. Okay, meanwhile, the wire vibration amplitude is something like 10 microns, and we're getting these waves that have amplitude a millimeter, which sounds like a resonant effect, except that the frequencies don't match at all for resonance. Okay, so we have a couple of vague ideas that we're pursuing on what might be happening here, but I would love for anyone to tell me brilliant insight on this. Okay. All right, so what I want to leave you with is we can excite at least the lowest waves along a free vortex using our vibrating wire. The amplitude we can actually get to be comparable to the length of the vortex segment and hence the wavelength of the waves. And there are some characteristics that suggest that we may be seeing a transition to nonlinear behavior. So where we're planning to go here is, first, now that we've figured out how to get the circulation without rotating, we're going to move the experiment to a dilution fridge, where we will no longer be plagued by 3-hour hold times that make us limit what we can do to investigate a vortex line. Going to lower temperatures may prove to be interesting as well. We're also looking at adding a MEMS device in place of a bump to try to pin the vortex to a higher frequency oscillator, order of tens of kilohertz. That should help us to detect higher modes, and also it'll be much cleaner to separate the drive from the detection. And then we also have been playing with trying to continuously excite the wire, a very different mode, which would be much cleaner as far as the results if you don't have excitation that's a blast followed by nothing and so on. But we don't yet understand that mode nearly as well as we do the pulsed mode after decades of working on it. So thank you.
Thank you very much. Time for some questions?
Naive question. What is the damping due to? I missed that point.
What is the damping due to? So we believe that it's from the interaction with the wall, just because it's so many orders of magnitude larger than the damping you expect from bulk friction. And we have some models of what happens if you have a bump on the wall and a vortex is trying to work itself loose. I mean, on some level, we know that there's a force, we know that there's interaction between the vortex and the wall, because sometimes the vortex actually pins. And so our picture is that whatever that interaction is, if it's not quite strong enough to pin, it's instead causing some sort of damping force.
And you suggest that at low temperatures, the Kelvin waves excited somehow aid the depinning process. To what extent do you avoid vibration of the cryostat, which might generate Kelvin waves?
We haven't done anything special for avoiding vibration. Yeah, I mean, this could be some issue. What we know is that we definitely know that changing the parameters of what we're doing with the wire has a very significant effect. So I think that what we're doing with the wire is swamping any native vibrations.
But it might be at a different frequency.
True. Yeah, no, I'm more thinking of if we, yeah, so if I go back, okay, and then it stopped. I can't do anything anymore. There. Ah. Okay. So if I go back to here, this slope, if we pluck the wire less often, the slope becomes dramatically faster. Okay, so that's sort of an end level argument that the wire has a lot to do with it. So I guess that's sort of my answer.
Is there any amplitude dependence on how so okay, so
Yes, if we vary the amplitude of how hard we're plucking the wire, yeah, we actually have the slope here relates we related it to the amplitude of plucking the wire, the time between plucks, and the temperature. And we could collapse all of them onto one fairly noisy curve by just looking at how much wire motion, what the average wire velocity was, you know, with all of those different parameters.
And what about in the amplitude of the modes that you see?
Actually, same thing. Those curves at the end. Right. This no longer works. Nothing works anymore. Okay, there we go. Those curves. Yeah. So in fact, these were at 3 different amplitudes. They're not, and we don't vary. We haven't varied the amplitude a huge amount. We're limited on the top end because if we drive the wire too hard, we start to blast normal fluid all over the place. And then if we don't drive, if we turn it down too much, then our signal to noise goes away. So.
Okay, any final questions? All right, thank you very much.